So the question is about matrix representation of the product C3 square I, where I is for center of inversion and C3 twice means the same C3 which is applied 2 times. Okay, so C3 one is what? If you consider anti-clockwise rotation, okay, if you consider C3 as a anti-clockwise rotation, then clockwise this clockwise is sorry anti-clockwise this way, anti-clockwise rotation by, because it's C3 so it is 120 degree, so clockwise it will be, so if you want to reach this point from A to B, anti-clockwise you are moving 120 degrees, but clockwise you have to move 120 plus 120, 240 degrees. Okay, so it is clockwise rotation by 120 degree, or sorry anti-clockwise rotation or by 120, or clockwise rotation by 240 degree. Fine. Then if you apply C3 2 means this is 1 and this is 2, that means it is anti-clockwise rotation by 240 degree, or clockwise rotation by from here to here 120 degree. Okay, so means we are asked about C3 2 into I. Now what is the matrix representation for I?
And 1000100.
No, it is negative. That is
Ma'am,
E. What you told
oh,
is
what you told is yeah, yeah, yes, ma'am. Yes, ma'am, I got confused.
hmm, I is
I is
center of inversion. It
Yes, ma'am.
Because what I does, if I is applied on any coordinate xyz, the result will be minus x minus y minus z. It inverts the coordinate. So if the matrix representation of E is I, like if I E is applied, then it will be as it is. So this is E is 1 1 1 and center of inversion I is minus 1 minus 1 minus 1. Now, so we have one of the matrix. Now we have to construct the matrix for C32. Now, last class we were discussing about matrix representation transformation matrix of rotation like Cn by any degree. Fine. Then for for clockwise rotation, we had for any Cn rotation, clockwise is denoted as minus. Uh, Generally, if it is Cn, it means anti-clockwise. If it is clockwise, then I am denoting it as minus, means opposite direction. Now, for C32 is what? Clockwise by 120 degree. Then the matrix representation for C32 will be, so instead of theta you have 120 degrees. Okay, now you can calculate the values for them. Cos 120, sin 120, okay. Now into D of I will be this matrix multiplied by the identity, sorry, center of inversion. Now the quick trick of multiplying this is that the diagonal elements become get the diagonal elements get multiplied. Since the rest elements in this matrix is 0, the that's when you multiply it with corresponding elements in this matrix and add it, it will be 0. So this and this, you multiply it just like this. This is simple matrix multiplication. So d of C32 into d of I will be, after multiplication, it is 1 by 2 minus plus minus plus. So this should be the answer. Now you can match which options are these. There is only one, there should be only one minus this one. Okay. The correct statements among the following are: elements of an identity matrix form Kronecker delta. Do you know what a Kronecker delta is, Nafa? Kronecker
No, ma'am. I don't know what that is.
Kronecker delta is just a class of matrix. It is denoted as like Greek letters like this and I and J. So this is an element, this is how we denote element of a matrix. I is row number and J is column number. Okay, so what a Kronecker delta matrix is, it is said that this element, this is just an element of a matrix, we are denoting it with this symbol, like we denote matrix by Aij, A, suppose R, M, like that. So this is just an element of a matrix. This has a special symbol. Now delta Ij, that element will be equal to 1, will be equal to 1 when I is equal to J, and will be equal to 0 when I is not equal to J. Okay, I equal to J means the row number and the column number is same. Suppose third row, third column element, fourth row, fourth column element, like that. So what does this means is, these elements are diagonal elements, principal diagonal elements. Okay, so del delta 1 1, delta 1 2, delta 1 3, delta 2 1, delta 2 2, delta 2 3, delta 3 1, delta 3 2, delta 3 3. Suppose I am writing a matrix 3 cross 3 matrix, okay, and this is delta ij for 3 cross 3. Now you see when I is equal to j, I is row number, means I is decided by this side and j is column number, so j is decided in this side. These are j's and these are your i's. Fine, row number and column number. Now you see when I is equal to j, means suppose for the first element I is 1, j is 1, so I and j is equal. Okay, here I is 1, j is 2, these are not equal. Likewise, so you will notice then the second row second element is this, third row third element is third row third column is this. So what are these? These are the principal diagonal elements. And when these will be, what is the condition? That when I is equal to 1, the value of that element I and j is equal, the value of that element should be 1. Fine, so 1 1 2 2 and delta 3 3 is equal to 1. And the rest, when I is not equal to j, suppose like this, and the other elements, it should be 0. So basically this is an identity matrix. Okay, so the Kronecker delta is identity matrix of any order. I have written it for 3 cross 3. You can extend for 4 cross 4 or 5 cross 5 or n cross n, anything. So instead of writing this much of matrix, suppose I want to write n cross n, I will have to keep on writing this. Isn't it? I will have to keep on writing this here. So to make it a short form, it is just written that it's a Kronecker delta, delta ij. It's equal to 1 if I equals to j, and it's equal to 0 if I is not equal to j. So the first statement is true, that elements of identity matrix form Kronecker delta. Understood?
Yes, ma'am.
Okay. Now tell about the others. What do you know about, how many types of matrices do you know? So here you have symmetric, Hermitian, unitary. Do you know about all these matrices? What are their properties?
Yes, ma'am.
Okay. Then What is a symmetric matrix?
Ma'am, like A is equal to A transpose.
Hmm. So, symmetric means when you transpose it, it should come as the original matrix. Like A is equals to A transpose. Means you swap I and J, then it will be equal. Aij is equals to Aji. This means A is equals to A transpose. So this itself is the definition of a symmetric matrix, that it is equal to its transpose. So this statement is also correct. And next is Hermitian matrix. What is Hermitian matrix?
A is equal to A transpose conjugate of A transpose.
Yes. So
Yes.
A is equal to A transpose conjugate. A transpose conjugate, and this whole thing is written as A dagger. Okay. Transpose conjugate or conjugate transpose. This is also written as this. It does not matter which operation you apply first, either you do a conjugate and then transpose, or else you do a transpose first or then calculate the conjugate. Okay, so in Hermitian matrix the diagonal elements are real. Okay, have you studied quantum mechanics?
No, ma'am.
Okay, okay, fine. So I'll just let you know this thing, that in quantum mechanics we use operators. Suppose in classical mechanics, if you want to calculate momentum, right? How do you do? You will have some formula, right, to calculate the momentum. So
Yes, ma'am.
in quantum mechanics also uh, you will have some operators, mathematical formula which we call as operators, that when we apply on something it gives the result of that. Suppose you need kinetic energy, you want to know the kinetic energy, you will have a particular formula to calculate that, that is called kinetic energy operator. You need to calculate the total energy, that will be sum of kinetic energy and potential energy, and then uh, we will have different formulas, one for potential, one for kinetic, like that. So any of these operators which we use in quantum mechanics are all Hermitian operators. Now, first of all, these operators are also matrices. And why they are Hermitian is because of this property. Diagonal elements are real. So when we apply these operators on any operand for so, then it gives its eigenvalues. and the eigenvalues are the values which we measure through experiment. So what we measure through experiment must be a real thing, right? It cannot be an imaginary. Suppose you want to know the kinetic energy of a gas, that kinetic energy cannot be an imaginary number, right? It has to be real. So that's why these operators are Hermitian operators, because they are diagonal elements which also gives the eigenvalues that are real. Okay,
Okay.
I know you have not understood, like you have not read quantum mechanics, but you should get some idea that this what you study in maths or in class 12th or so, these things are utilized in some way or the other in these concepts. Okay,
Yes,
so you
ma'am.
should just, I'm just trying to interconnect these things.
Yes, ma'am.
Okay, so diagonal elements are real. Off diagonal elements can be complex or real. Okay, let us suppose this is an operator. Sorry, this is a matrix. How will you prove that this is Hermitian?
Ma'am, you should do those operations and then check if it's equal.
Yes. So let us do the transpose first. If I do the transpose of this, I will get 3, 3 minus 2i, 3 plus 2i, and 2, right? Then if I do a conjugate, so the conjugate of a real number is equal to the number itself. Then in imaginary number, the sign changes. Now these two matrices are equal. So this is an Hermitian matrix. Also there are some properties for Hermitian matrix. The first one which I told, that diagonal elements are real. And the other way of saying this is that the determinant of that matrix will be real. Determinant or eigenvalue of the matrix is real. This is the first property. Then the other properties are like the sum of any two Hermitian matrices are Hermitian. Sum of any two Hermitian matrix is Hermitian. Third is product is also Hermitian. Like if you have two matrices which are Hermitian, then their product will also be Hermitian. And the fourth property is inverse of a Hermitian matrix will be Hermitian. Okay, and one more property is that suppose in a Hermitian matrix, if this is a Hermitian matrix, if it doesn't have any imaginary, it doesn't have any imaginary number, what will happen if you do a transpose and then conjugate of that?
Like the value will be equal.
Yes, the values will
Yes,
be
the
equal.
value.
A, A star is equals to A if A is real, right? So if all the elements are real, the matrix will, that Hermitian matrix will become a symmetric matrix. A symmetric matrix is what? A is equals to A transpose, right? And Hermitian is, A dagger is A transpose conjugate. Now, if A, this is equals to A itself or A conjugate transpose, right? So, if A star is equals to A for real elements, this will become then A dagger is equal to A transpose, which will be equal to A. This is what as when all the elements of a Hermitian matrix are real, that matrix becomes a symmetric matrix. So this, the correct statement it is asking. So a Hermitian matrix has real, always has real elements. This is not true. It can have complex elements. It is not overwritten that it should contain diagonal real elements. So the diagonal element has to be real, but the other element can be imaginary. So this statement is not true or partially true. A fourth one is adjoint of a unitary matrix is its inverse. Adjoint is what? Again, conjugate transpose. Unitary matrix is defined as it its adjoint is its inverse. So if A is a matrix and A dagger is its adjoint, then if you multiply those two, you will get an identity. Means A is equals to 1 over A dagger. Adjoint is its inverse. Or you can write at adjoint is inverse. So if you find the inverse of A, that will be equal to its adjoint. So this statement is correct then. Adjoint of a unitary matrix is its inverse. Okay. Now A, B, C and D are real positive numbers with D is its determinant A square plus B square plus C square plus D square, and you have to find the inverse of this matrix. A plus IB, C plus ID, A minus IB. Its determinant is A square plus B square plus C square plus D square. How do you find inverse?
1 by determinant A into adjoint of.
Yes. So is equals to 1 by determinant into adjoint of A. Then can you figure this out?
Yes, ma'am. Ma'am, actually, I solved this before, and I think there is some discrepancy in the question because my answer wasn't there in the options. I guess like it's supposed to be A minus IB or something, and then I got the answer, and it was correct also.
A minus
A
IB, the first
minus
element.
IB. The first one.
Okay.
Okay.
So you are telling that the
So
first
you're
element should be A minus IB.
I'm guessing, ma'am, it was a long time ago, but there was some problem with this question. I remember that.
Okay. Maybe it can happen that like there can be misprint in the options. So, but you know the process, right? How do we do it?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So to get the adjoint, what we first calculate is cofactors. Adjoint matrix is what? Transpose of the cofactor. Now cofactor, let me write cofactor by C. C11 is equals to, if we are calculating cofactor for this, it will be the rest of the element. So cofactor matrix is this. Let me know if I'm doing anything wrong.
Okay.
Now we have to transpose this. Okay. Then is this is not given in solution?
No, ma'am. It's the first element is A plus IB in those solutions. So I'm guessing it should be A minus IB in the question.
Hmm.
Right.
Okay, but whatever we are getting is this only. A minus IB by D, but there is no A minus. Hmm. Yeah, okay, you might correct. They can be misprint, okay then. But you have submitted the assignment, no? What does that solution say? Does it like consider it?
Yeah, ma'am. I just did the same question with A minus IB and I got the answer.
Okay,
I
okay,
the
okay.
answer is A.
A itself.
Yeah.
Okay, fine. Fine. Okay then. Shall I move ahead then? You're clear with this,
Yes.
right?
Yes.
Wrong question. Fine. Then a matrix. I think today's assignment is very easy.
Easy.
Like
Yes.
a matrix is singular when its determinant is necessarily
Zero.
zero. Yeah, that's it. Zero. And determinant is not defined for what type of matrices?
Not defined from. If determinant is not equal to zero, it's non-singular. I'm aware about that, but
No,
that is
for okay, you can calculate determinant only for square matrices. Matrix can be rectangular, right? When rows and columns numbers are not equal.
yes, ma'am.
But for that you cannot define a determinant.
Okay, ma'am.
Then for singular matrices, for suppose you have been given a matrix, and just by looking at it, what are the ways you can tell that whether it's a singular matrix or it has some value of determinant? There are some
And by looking
properties
at the
for
first
singular
row or
determinant, right?
something, I measure by checking the elements of the first row.
Any row you can check. So there are some properties like if any two rows are equal, rows or columns are equal, then that determinant will be 0. Means it is singular. Okay. Next one is if any row is multiple of is a scalar multiple of another row, then the determinant will be 0. Then determinant is 0. Fine. Uh, then if you have matrices like this, what is it? This is called null matrix. So a null matrix determinant will always be 0. Fine. Uh, and also for singular matrix, inverse is not defined. Why is it so?
Because 1 by 0 is not defined.
Yes, because 1 by
Yes.
0 is not defined. For calculating inverse, you need to do 1 by determinant. But if determinant itself is 0, 1 by 0 becomes an undefined number. Okay, so by looking at the matrix, if you can figure out if two rows or two columns or any number of rows or columns are equal, then that will be a singular matrix. And if any row is scalar multiple, suppose you have 1 2 3, then you multiply it with 3 like this. If this is the determinant, what you can do is, so it should have some other numbers here as well, it should be square. What you can do is you can just take out a common multiple from this row. Okay, you can take out 3, then it will become same, right? So now it satisfies this property, first rule, that two rows have become equal. This is then a singular matrix. Understood?
Yes, ma'am.
Okay, unitary transformation of a unitary matrix always gives a matrix that is
Unitary.
unitary. Yes. So it's just same property like the Hermitian one which I told, that the product of two Hermitian matrices or the sum of two Hermitian matrices is Hermitian. It's like the same thing, that when you do a unitary transformation on a unitary matrix, the result will be another unitary matrix. Okay, then of the following, the quantity that is not an eigenvalue of this. You know how to calculate eigenvalues?
Ma'am, I know, but I have to revise. So for this question, I just what I did was the sum of eigenvalues is equal to trace. So with that, I calculated.
Okay. So how did you do that?
Like sum of eigenvalues is equal to cos theta plus 1. So that is 2 cos theta plus 1.
Hmm.
And then I took the values from the option and just like eliminated which one doesn't
Okay.
add up.
Okay. Okay. Yeah. That's a smart move. So there is a general way to calculate for any matrix, which suppose this is a 3 cross 3 matrix, a smaller matrix which is like easier to do like that. But generally what you do is you take, suppose this is the matrix denoted by A, you take this matrix A, then subtract lambda times E. Now E is what? Identity, and lambda is what? A some number which is not
Yes, ma'am.
defined yet. Okay, and then you take the determinant of it and equate it to 0. So this is what we call as characteristic equation. So now lambda times E is, so here we have 3 cross 3, so I'll take a 3 cross 3 matrix. This is E. Okay, then if I have to multiply it with lambda, it will become lambda 0 0 0 lambda 0 0 0 lambda. Fine. Now you have to subtract this from A. Basically it becomes as you have to subtract the diagonal elements, subtract lambda from the diagonal elements. One minus lambda. This you equate it to 0. Now you find this determinant. Once you do that, you will get an equation, cubic equation. So cos theta minus lambda. Here we have cos theta minus lambda 0 0 1 minus lambda minus, this sign is important, minus sine theta. Next you will have minus sine theta 0 0 1 minus lambda, then plus is 0 into the other things which will be 0 only, and then equate it to 0. When you do this calculation, you will have this equation minus and this part, this term is 0 anyway, equal to 0. So you can take 1 minus lambda common here. It will be cos theta minus lambda square minus minus is plus sine square theta, this equals to 0. So from here you will get 3 values because it's a cubic equation. So on solving you will get 3 values of lambda. Those 3 values should be, if you solve this will be 1 minus 2 cos theta lambda cos square theta equals to, now equate. So from here, from this term, one value is lambda equals to 1. This is one root. Fine. And from this quadratic equation, you will get two roots, which is cos theta plus minus I sine theta. These three are the eigenvalues. Out of the following the quantity that is not an eigenvalue. So not an eigenvalue is minus 1. Minus 1 is not the eigenvalue. So this is the general way we solve for eigenvalues.
Yes, ma'am.
A and B are real positive inverse. This you did last time, right?
I know how to do it, ma'am. So,
This I think this question was there last time also, last week when we were discussing inverse of A minus B, B, A. Determinant is A square plus B square.
plus B square.
And for inverse, you just
Okay, yeah,
interchange.
okay, ma'am. Yeah.
Okay. Then adjoint matrix. Adjoint is equals to 1 over determinant, then cofactor transpose. So determinant is 5e. Oh, it is just, oh, sorry. It's not asking inverse. It's just asking adjoint. So we have to just find the cofactor transpose matrix. C11 will be 5, 1, 2 will be minus of 8, 1, 2, 1 will be yeah. No answer matches, no option matches with it. No, no, I think B is the correct. This is minus. Minus. Is this correct?
Yes, ma'am.
Again, the eigenvalues. Can you do it now?
Yes, ma'am.
So, how will you start? Simply is 2 minus lambda, 4 minus I, 4 plus I minus 14 minus lambda. Just from the diagonal elements, you subtract lambda equals to 0. Then find roots. You will get two values. One will be eigenvalue include. So it should have any two of these, because it will form a quadratic equation. Anyway, it's a 2 cross 2 matrix. So it should have two eigenvalues. Number of eigenvalues are equal to the order of the matrix.
Okay, ma'am.
So what is it? Answer. Have you done it already or you are doing it?
No, ma'am, I've already done it. It's minus 15 and 3.
Okay, fine. So it's minus 15 and 3. Simple, no? But 2 minus lambda minus 14 minus lambda minus 4 minus I 4 plus I minus 28 okay, if you solve it, it will be minus minus this is plus 14, no, plus 14, so this is plus 12 lambda minus this is 17 and minus 28 minus 45. So answer should be or some you have already told the answer is 3 and 15. I'm not calculating it more. 3 and minus 15. Minus 12 plus minus under root 12 square minus 4 times so if you take minus 12 minus 18 by 2 or minus 12 plus 18 by 2, then this will give you 30 by 2, so minus 15, and this will give you 6 by 2, so 3. Yes, you are correct. Is the answer. These are the eigenvalues. And then how will you write the corresponding eigenvectors?
Is it A lambda x or something?
Hmm. This you write at A minus. So now you have found the values of lambda, like eigenvalues you know. So this is first eigenvalue. So this will give you first eigenvector. The second eigenvector will be A minus lambda 2 times E equals to 0. This will give you a second eigenvector. So then you can write xi x1 x2. Okay, and then you can put these values of lambda. Suppose you've got 3 in 1, so your first equation will be a minus, so the diagonal elements will be a minus 3e and x equals to 0. X1 you are taking, right? This should be I1, this should be I2. So your I will change, and 1 denotes that this is the first eigenvector. So I1. It should have, I will go up to 1 to 3 because this is a 3 cross 3 matrix. So this will be a, it will have 3 elements. So your X should have 1, 1, 1, 2, 1, 3. Oh, sorry. 1, 1, 2, 1, 2, 1, 3, 1. This should be a 3 cross 1. This should be 3 cross 3. When you will multiply, it will become a 3 cross 1 matrix. So those three x values will define the eigenvectors. Okay.
Yes, ma'am.
So I think this is it for today's. It was an easier assignment.
Yes, ma'am.
Are you watching the lectures?
Yes, ma'am, but I'm a bit slow right now because of college. I have to catch up.
Okay,
Okay,
okay, it's fine.
okay, it's fine. Ma'am, is there any other book other than F.A. Cotton? Like something that is more easier to understand?
In the first lecture, I gave you some books, right?
Yeah. Okay, ma'am, fine. I'll go through
Just
that.
check it. What I gave you, like Bishop, some
Okay,
book
ma'am.
list I gave.
Yes, ma'am. I've noted it down. I'll go through that.
Hmm.
Hmm.
You can download those books. That is like
Okay, ma'am.
more written like in a more friendly way. Or there is another book by, I just forgot the name. I
Just
might
what
have
the
written it somewhere. Or you can look at Atkins also.
Okay, ma'am.
Group theory is there in every physical chemistry books.
Okay, ma'am.
If you need little bit of maths then matrices, then you refer to 11th and 12th standard matrix book, like mathematics book, which discusses chapters on matrix and set theory, like that.
Okay,
But
fine.
that is not needed much. I mean, this much matrices and all what you know is enough for doing this. You just need to know how to multiply the matrix correctly. That's all. The rest is not needed.
Okay, ma'am. Fine.
Okay. Okay, then I'll upload this in the drive.
Fine.
Okay, Nafa, if there is nothing, then I can close the session.
Okay, ma'am. Thank you, ma'am. Good night.
Yeah. Good night.